Functional Programming Primer by Deepu K Sasidharan. Did I pronounce your name right? I'm sorry if I didn't get
Close
it
enough.
right. Yeah, it's enough. Close. Thank you very much. Thank you very much. And you're with us from a link, actually, from Utrecht in Holland.
Sorry?
Yeah, you're with us from Holland.
Yes. From Utrecht.
Yes. So I'll hand over to you, and you can start your presentation.
Okay. I
thrilled.
probably have to run a bit faster. I did have
no
something
worries.
else later coming up.
No, you take your time. We will have time. We don't have a curfew police.
I have to finish faster, probably.
Oh, you have to finish faster. Yeah. Okay.
Yeah, because I thought this would end at 8. So,
yeah.
Cool. Okay. So I'm going to start. As introduced, my name is Deepu K Sasidharan. I'm the co-lead developer of JHipster. So if you are in the Java community, probably you have heard of it or used. It's a rapid application development platform. Also supports Kotlin, Node.js, a few other stuff, .NET and stuff. I'm also a developer advocate at Adyen, a fintech company based out of Netherlands. I know it's aficionado and polyglot dev as well. So you can find me on social media. I also wrote a book if you're interested in JHipster. So let's get into functional programming, right? So before we get into functional programming specifically in Java, I want to say that this is also aimed towards people who are not very familiar with functional programming, especially in Java. So slightly beginnerish. So if you're a Java expert or if you're already a functional programming expert in Java, then this is not the content for you. If you are interested in learning about what are the different things that you can do within what is provided by Java in terms of functional programming, then this might be for you. So before we talk about Java, we quickly have to refresh the basic rules of FP, right? Probably most of you already know this, right? So these are like the golden rules, right? No data mutations and no implicit state. So this kind of translates to no side effects and pure functions only, right? So in practice, so an operation should not change any state outside of its functional scope, and a function should be idempotent, right? So a function should return values based only on the arguments. It should not be referring to external state. It should not be modifying external state. So these are what roughly it translates to. So this context is required for the content that we are going to see. It's also important to set some expectations, right? So there is a difference between a functional language versus a functional style language. So a functional language is not the same as a functional style language. For example, Haskell is a pure functional language. So it does not allow mutations of state or side effects, and it forces you to write declarative functional code. So that's a pure functional language. Whereas a functional style language allows you to write functional style code, but does not force anything or does not help you along the way, or does not make your whatever you write automatically conform to the golden rules of functional programming. So the ease of doing functional or declarative style coding, whatever you want to call it, in such languages really vary based on the features provided, based on what the language is, right? For example, it is much more easier to write immutable or declarative code in Rust or Scala or even JavaScript than in Java. So those languages can be called as more functional style languages than Java, right? So I'm not a functional zealot because I'm a polyglot developer. I use at least 4 to 5 languages a week. So I cannot afford to be a functional programming zealot and be productive at the same time. So that's not. I found that not to be possible from experience. So I like to mix and match paradigms based on the language that I'm working on and based on my use case. So I try to write declarative code as much as possible without having to work around or having to heavily modify everything just to conform to the functional rules. I don't do that. And I personally haven't used or am interested in any pure functional languages. I've found them to be too pediatric, or I don't know. I never really like them. So I'm more in into functional style languages, which I find nicer for how I like to do stuff. So from based on that, so there are certain things that makes a language a functional style language, or even a functional language, right? So if it conforms to all of that, then probably it's pure functional language. If it can do these things in some way, then they are functional style languages. So basically you need to have like a strong type system, functional data structures, and so on. So we'll look into each of this. All right. So from that in mind, we can call Java a functional style language. Of course, you can do a lot of these things in Java. Of course, we are talking about the latest version of Java, or kind of like Java 8 onwards. So let's look into each of that. So we'll get out the no-brainers out of the way, because we don't have to explain. I think I don't have to explain this much to most of you. If you are even a Java beginner, probably you understand most of these things, so doesn't need much introduction. So Java has a strong type system, right? So there is nothing much to worry about there. So we can just get that out of the way. So it has a strong type system. It has great generic support. It can do local type inference with the var keyword, Java 11 onwards, and it can also do type inference in Lambda arguments, right? So it conforms to the type system requirement. So that's like a tick for us. So the second thing that it conforms to is functional data structures. So when we are doing functional programming, certain data structures are better than others. For example, stacks, maps, and queues are better than arrays, or stuff like that. So from that aspect, because Java is highly, statically typed, it has a great inheritance support, and it supports polymorphism. So it is easy to build data structures in Java as the way you want. So that means you can build any kind of functional data structures. It also provides most of the standard functional data types like stacks, maps, and queues out of the box. So it's a tick as well. So we are just getting these out of the way. Pure functions. So when it comes to a pure function, it's quite simple, right? So you basically get some input, it produces the output, and it has to be output. And that means for the same set of input, it always has to produce the same set of outputs without side effects. So you can, of course, do this in any language for that matter. And of course, you can do that in Java as well. The only problem is, unlike Haskell or even a language like Rust or Go, Java is not going to help you at all to make sure that you're writing pure functions. So you can write, it's up to you. It's on to the developer to make sure that your functions are pure, doesn't do accidental mutations and stuff like that. So Java doesn't help you at all there. So that's why this is not like 100% support, but you can still do it. Java just doesn't help you there, but you can still do pure functions. You just have to be more disciplined, and you have to pay more attention, right? So the next thing, so I think this is like the most important thing when it comes to functional programming is, of course, functions as first-class citizens, or higher order functions if you want to give it a fancy name, right? So this is a mixed bag in Java. For a function to be first-class citizen, it should be acceptable as a variable, or as a function argument, and also should be able to be returned as from a function, right? So Java functions are not first-class citizens in Java. You cannot pass Java functions into a method, or you cannot return Java functions from a method. So this was until Java 8. From Java 8 onwards, we have something called Lambda expressions that can actually bridge this gap. So let's take a closer look at what Java expression is. So I'm going to switch to editor for this. Let's see. So we have this quite simple Java code. I'm going to zoom it up a little bit if it is. Second. I think this is good enough. Yeah, seems good enough. Probably smaller here. Okay, so this is just basic Java test class. So we create a thread, we create a new thread, and we declare a new runnable. So this in Java is an anonymous inner class, right? So basically you implement an interface right as into the argument. So this is possible in Java, even before Java 8. So this is quite common in Java. So if you run this, you can see that it prints out both these hello world statements. So as you can see, I'm using IntelliJ IDEA here, and you can see it already shows some suggestions here. So it says I can convert this with a lambda, right? So what does that mean, right? So basically, a lambda is nothing but syntax sugar for removing some of the noise from a construct like this, which is an anonymous in a class. So basically, this is noise, right? Because we are passing something to a thread, and we know from the signature of the thread that it has to be runnable. So so we know this, and the compiler also knows this. So we can actually remove that, right? So the same here. And what else is noise? So this is also noise. It knows that it has to be overridable. So let's remove the noise. So public void run again. It's a declaration of the overriding the interfaces method signature. So again, this is noise. So let's remove the noise. And what do we have left? It's a method name, the arguments, and the method body, right? Again, if you have to remove stuff from here, what is useless? So this name doesn't help us in any way. It's quite useless, right? So if we do this, we are left with the argument list of the function, the function's body, which might or might not return something, right? That doesn't matter. That's from the function body. So we are left with this. So now we add an identifier to separate the method from the argument list from the body, and that's it. So this, if you run this now, it's compiling and it prints out the same thing, right? So this is basically a lambda. So here we can do a bit more cleanup, and just since it's a single line expression, there is a little more syntax sugar that we can do. So we can remove the braces here and the semicolons, and this becomes much more nicer. So this becomes, let's remove this and this, right? So this is what basically a lambda is. So it still does the same thing. It still runs and prints out the same thing. So this is what a lambda is, right? So so objects are first-class citizens in Java. That means objects can be initialized, passed inline to as method arguments. So Lambda is just a syntax sugar on top of this already pre-existing Java stuff, and now we are able to pass this really nice-looking lambdas, or equivalent of what you would call closures or whatever, right? So this is how we can actually get higher order functions. So since a lambda is a syntax sugar of an anonymous function, it can be passed as an argument, it can be returned from a method, it can be assigned to a variable. So it conforms to everything that a higher order function should do, right? So this is what we would use as higher order function in Lambda to do functional programming, right? So what else can we do? So this is quite simple example. What more can we do? So Java also gives us a way to create our own lambda functions. Since Java is strongly typed, everything has to be predefined, right? So it gives us something called functional interfaces. So we can declare our own functional interface. The annotation is just for documentation. It really doesn't do anything. It just to indicate that it's a functional interface. So basically, you define an interface and you define some methods in it, and you can pass this interface as function arguments. You can instantiate them inline, and the lambda syntax sugar allows you to make them into very readable and nice looking expressions. So let's look at let's look at an example. Okay, so So we have a array list here. So bigger. Is it visible? I think so. I'm going to make it a slightly bigger. Yeah, good enough, I think. So we have an array list, and let's say we want to create a method called map for each, so which basically iterates and maps the elements of this array. So what we are going to do is, first we created this functional interface, right? It takes two generic types. So basically it has one method declaration. So it returns type S, and it takes an argument of type T. So it's declared as a functional interface. And then we have a method that takes a list as a first argument and this interface as the second argument. So within our method body, we create a new array, we do a for each on the array, and for each element of the array, we call the method execute from this interface that we are passing, right? And so the return of that is added to the array, and then we just return the array. So it's simple as that. And in our main function, so we are passing this list, and we are creating this inline anonymous function based on our function factory, right? So again, we can do the simplifications here to, so this already works. So let's just quickly run it. So it already works. So we can follow the idea's suggestion and replace this with a Lambda, right? So this looks much nicer. So now all the noise is reduced and it looks much nicer. We can go a step further and we can remove also this type information because the compiler already knows it. So again, still works as the same, right? So much more nicer. And we can go even a step further, and actually we can replace the Lambda with a method reference. So it's nothing but replacing whatever the method is called by its reference. So basically for this, we'll be replacing it with string long length because it's of type string, and we are just calling the length method from the standard string implementation. So this also does the same job. So we are able to define our own Lambda, and we are able to make this call much more nicer and much more functional, right? Now we can actually don't even have to do this. We can even use some stuff that Java already provides. For example, let's go here. We saw this. So Java already provides built-in functional interfaces, which can be used for most of the generic use cases. For example, there is unary operator, which takes a single argument and returns value. Both argument and return is of the same type. We have binary operator, which takes two arguments and returns something, and everything is of the arguments and return will be of the same type. Then we also have a function which can take an argument and return something, and the argument and return can be of different types. Then we have a consumer which takes a single argument but doesn't return anything. So basically executes some sort of code, can be used when you have side effects and stuff. And then we have predicate, which takes a single argument and only returns a boolean. So basically to do tests and stuff like that, assertions and kind of thing. We also have supplier, which does not take any argument but provides a return. This is useful for doing computations. So like if you want to return a random number, or if you want to calculate something based on some logic and return something, then you can use a supplier. So these are the inbuilt functional interfaces under Java util function that we can use. So now let's see what we can do with that. So for our example that we saw, we can actually remove this. We don't need this, and we can just convert this to function, and we call the apply method because that's the method name defined, and it still does the same thing, right? So this is how we can use the built-in functional interfaces. Java also provides a lot of higher order functions built-in higher order functions as well. For example, the util collections package has a lot of methods that accepts lambdas, like sort, binary search, min, max. All these can accept lambdas. Some of these are so yeah, sorry. Then we also have the Java util stream, which was introduced with Java 8. So this package provides a lot of methods that accepts higher order functions, and they are chainable, and that means we can use these as pipelines to write pure functional code, and most of these functions are pure functions. So we have the generic things that you would expect from functional languages, like map, reduce, filter, find, for each, so on and so forth. Then we also have the optional package, which provides, of course, the optional implementations. It also provides functional methods like if present, or else, filter, map, and so on. So you can do a lot of stuff with optional if you want to avoid null, because null is not something that everyone likes in Java. So if you want to avoid that, you can also wrap everything in optional and make sure that you don't have to deal with nulls, and you can do more functional coding there. Also, any interface that any Java implementations that accepts an anonymous class as a method argument can also take a lambda in its place. So that's also possible. So let's see if we can use those with streams. So with streams, we can do a lot of things. For example, with the same list that we had, right, that we did here, we can also do the same thing with the inbuilt stream. It's quite easy, right? So we just need to use the stream method for list. It provides us with all the niceties from the stream API, so we can map, reduce, do all of that. So we can make it a bit more nicer, this one. And similarly, we can also do filters and stuff. You can also make this nicer to string uppercase, right? So this does everything without even having to write functional interfaces ourselves, right? And another advantage of the stream interface is that you can do parallel computations. For example, here we are generating 5,000 integers, and we are doing some pipeline on it. We are filtering it, we are mapping it to with mathpow, and we are reducing them. This can be done in parallel, actually, and this would be helpful to improve the performance when you are using these kind of pipelines. So I'm going to replace some lambdas here, double sum, to be nicer, and let's execute this. So everything works as expected. So the Stream API offers nice ways to write functional programming in Java, mostly using lambdas, and it makes it lets us write more expressive and declarative code. Let's see what else we have. So pure functions and higher order functions, not perfect, but doable, right? You just need to have some discipline, and it's still doable in Java. Next up is closures. So let's see what we can do for closures in Java. Let me go back to my examples. So a closure is basically a function that can capture its scope, right? It is possible in Java, but not with standard functions, but with lambdas again, of course. Everything functional in Java is done with lambdas. So I have this method called add here. It takes an argument, and from this add, I'm just returning new function, an anonymous inner function, right? So we will see this off again and again. So anonymous inner functions. So I'm sorry, anonymous inner class. I'm returning a new anonymous inner class of type function of integer, and then let's see what I can do with that. I'm going to format this a bit, right? So then what I'm doing here is I'm going to curry this. I'm using this add here, right? I'm creating a new closure app. I'm calling add with a predefined value. So I'm passing 10, 20, and 30 here, and I'm assigning the returns as new functions. Then I can execute the new functions and apply more values to it. thus creating partials. So these are my partial curried functions, and I can pass more values and execute them to create variations. So this is how we can do currying in Java as well using closure. So this closure is already capturing this value, which is passed as the argument, and using that when we are doing the apply. So it can already memorize its scope. So we can make it even more expressive. Let me remove these comments just for to be cleaner, and I'm going to replace with Lambda, right? So this is now much more expressive and much more nicer. So and this one also actually can be, I think this can be replaced with unary or binary operator. Yeah, this can be replaced with unary operator as well. I'm not going to do that. This is also fine. But you can, if you replace with unary operator, then you just have to provide one generic type argument. So that makes it a bit more nicer. So let's execute this as well, just to make sure. Yes, and you can see that it produces different results based on the curried functions. So that's about closures and currying, right? So yeah, we saw currying. So using these techniques, so using higher order functions, using lambdas, closures with lambdas, and with currying, we can do a lot of functional programming in Java. So I would say you can even get away with doing mostly functional programming just by using these. The only caveat is you have to have the discipline, because Java is not going to help you, in a lot of ways like Haskell or Clojure does. So it's going to give all these things, and it's up to you to make use of them properly. Right? It's up to you to avoid mutations. Of course, you can write a lambda and do all your state mutating code there. Java is not going to say anything. It's up to you. So that's the only caveat here. So let's look at recursion now. So again, another thing that we normally do with functional programming. 1 second. Yes. So normally do is avoid imperative code, right? So for loops and such is the most used kind of imperative code, right? So how do you avoid that? Of course, with recursion. So so recursion is possible in Java, like any other language. In every language that has functions, it is possible. But the real question is when to use recursion and when not to use it, right? So let's look at some examples here. So I wrote this simple factorial, right? Of course, factorial is the most common recursive problem, right? So a simple factorial function. So I have this long factorial function. I'm just calling it with a value, and it produces the output. I benchmarked this using JMH, which is the Java micro benchmarking harness. And this traditional iterative approach. So this is the imperative iterative approach, right? This produces close to 10 nanoseconds per operation. So that's quite fast. So I went ahead and rewrote the same thing using recursive approach. So I basically added, changed that function and call it recursively. Produces the same output for the same value, but now it takes close to 20 nanoseconds per operation. So the performance has become half of what we have with imperative code. Of course, this is expected, right? Because recursions aren't great for performance, because they add a lot of additional load to your stack, because the stack has to remember each of these function calls. It keeps that in the stack memory, and it is quite easy for you to get out of memory exceptions from these. Stack overflow exceptions from these, which is quite common in languages like Java. So when performance is paramount, or if the number of iterations are going to be a lot, and if you know that already, then probably recursion is not ideal here, and imperative code would be much better here, because imperative code is more low level. The stack is not overloaded like in recursion. So I would normally go with an iterative approach within a pure function, so that everything, all those mutations and stuff is within that one function, and with good test cases, then recursion when performance is paramount. There is also another option. Another option is to go with the tail recursion approach. So for a tail recursion approach, we use multiple methods so that the intermediary method doesn't have to be in your stack. So the compiler can drop that safely without issues, and your stack will not be overloaded. So with a tail recursion approach, you might not get stack overflow errors like in the normal recursion method. Um, but still the performance is not as great as pure iterative method, because this is still not as low level as normal for loop, right? You're still adding abstractions, and unfortunately language like Java doesn't offer zero cost abstractions like Rust or something. So once you start adding more abstractions, it's going to add to that performance cost, right? So many languages, like especially functional languages like Scala and stuff, will optimize tail recursions. So it means if you write recursions in this style as tail recursions, it will automatically optimize that code on par with the iterative code. So in those kind of languages, you can get away with writing tail recursions, and you never have to write iterative code, and you still get performance as close as your iterative approach. But unfortunately, Java doesn't support tail recursions. So this kind of refactoring to do tail recursions will still give you better performance. For example, here we had close to 10 nanoseconds per operations. Our normal recursions had a double of that per operation, and this one has like in between that for operations. So if you really have to write recursion, then tail recursions are much better. I mean, regardless of language, tail recursions are always much better than plain old recursions, just to avoid stack overflow errors. We can also do the same thing using the inbuilt stream API, right? So it becomes a bit more okay, depending on how you like to read code. Some people might say this is much more readable than this. Some people say no, the other one is readable. Of course, if I made the arguments more expressive, then maybe this is much more readable. So that's probably on me. So this can also do the same job, but the performance is the worst. So I wouldn't recommend using the Stream API for recursion, because it performs the worst. I think it is improving slowly with each versions of Java, but it is still not as good as tail recursions or your pure imperative code. So ideally, for things that are very performance sensitive, I think iterative approach is still better if you make sure that you're not mutating data outside of that and stuff like that. It is still much better than writing something functional just for the sake of it. And if it is something trivial, then probably you can even go with the Stream API. But if it is something in between, then maybe tail recursion is a better option. So recursions are a mixed bag. It would have been nice to have tail recursions, and probably we could write much more expressive declarative code rather than unreadable for loops and while loops. But unfortunately, we don't have tail recursions in Java yet, and so we have only this. So next important thing for a functional language is, of course, lazy evaluations, right? So let's. So this is like a trivial example I was trying to do. So let me switch to. Before that, like when writing a lot of declarative code, as we saw with recursion, right? So every level of abstractions we make, we are adding some performance, small performance penalty. So unless you are working on a language like Rust or C++ or something which offers zero cost abstractions, you're always paying for your abstractions in languages like Java, or even Scala or Kotlin or whatever. You're always paying for the abstractions. And with the functional style of programming, you will be adding a lot more abstractions compared to imperative style of programming, because imperative is more low level than the functional style with more abstractions and stuff, right? So you are adding a slightly more performance overhead. So in order to in order to balance that, most of the functional programs also, functional languages also do lazy evaluations. So your methods are evaluated only when they are required. But unfortunately, Java doesn't do this. It does strict evaluation, except for ternary and short circuit operators. So in order for us to do lazy evaluations, we would have to work around. There is no direct way to do that in all places in Java, so we'd have to do some workarounds. So let's look at a sample here. So I wrote this like trivial program. I have this program called function called add or multiply. Takes in two values, and just if it is based on a boolean, it returns add or multiply. Of course, this is not a useful thing. You would never do that in real life. Just to demonstrate this concept, because this is because to do lazy evaluations Java takes a little bit of convoluted coding and stuff, so probably is not the most readable thing to do. So a sample like this probably might be easier to understand. So I have this simple methods which just adds and multiplies. So let me run this. So when I run this, you can see that it is executing add, multiply, and it is executing add and multiply for both. So for both cases, regardless of what you do, it is doing evaluation of both functions. That is because we are just calling the functions as parameters. So it's always evaluated. So there is no lazy evaluation here. The only way in Java to kind of achieve something closer to that would be to convert to something like this. Again, Lambda comes to our Lambda comes as a savior here. So what I rewrote is, so for the add or multiply method. So let's look at that here. Let's look at the add or multiply here. It's quite simple, right? But in our lazy sample, we have replaced both the arguments with the functional interfaces, so that we can pass lambdas there. That means we have to provide type information so that we can pass different types, and those can be inferred using the generics. So now you see that this is a higher order function as well, because it accepts two lambdas. I mean, pseudo higher order functions, because it's not really higher order. It's not really accepting functions, right? It's just accepting interfaces, which kind of emulate or look like functions when using the syntax sugar. So it's like a pseudo higher order function. And we changed also the add and modify method, multiply method. So now the add method is also a lambda instead of a normal function, because we cannot pass normal functions here, right? So but since it is a lambda, we can also assign them to a variable and almost use it the same way. So if you look at the eager sample, the add and multiply functions compared to the lazy sample hasn't changed. So it looks still this almost similar. It's still readable, right? And I would say it is even nicer, because we could get rid of some type information noise, which the compiler could infer anyway, right? The only readability issue would be with this code, which was much more readable in our eager sample, which was quite simple, whereas in our lazy example, it has become a bit more, I don't know, unreadable kind of thing, with lot of types and stuff going on. So now what we are doing is we are making use of the fact that Java lazy evaluates ternary operators. So we are looking for our precondition. We are using the ternary on our preconditions and calling apply methods on our functions. So when we run this code, if you look at the output, so only add was called when it was true, and multiply was called when it was false. So this kind of solutions can be used to achieve lazy evaluations in Java, and unfortunately, these kind of convoluted solutions are the only way to do lazy evaluations. You can do that with ternary operators or the short circuit and or operators. It's up to you. But there is no what do you call, like, catch-all solutions here. So based on your requirements, you might have to do a lot of similar implementations. You might have to rewrite your code in such way. So ideally, for trivial stuff, it probably is not worth doing it. But if you have some use case where there are two you know heavy blocks of code which has considerable performance impact, and if your normal code is normal functional code, when you're trying to pass them, are not being lazily evaluated, because if you just pass them as arguments, they are not going to be lazily evaluated, they will be strictly evaluated. So you can kind of use lambdas to rewrite them, and with the functional interfaces you can kind of play around and kind of get a lazy evaluations. But again, on a use case basis, you might have to re-implement it per need, unless you have all your methods confronting to the same generic case. Maybe if you spend enough time, you can come up with a solution which is quite generic for a lot of cases. So from that angle, lazy evaluations are still it's not like it's still a mixed bag. So I'm as you can see, I'm putting some smileys. So type system and the functional data is like all good, like it's as good as any other functional language. And the other stuff like pure functions, higher order functions, and closures and currying is like, it's not like pure higher order functions or anything, but it's close enough. It's syntax sugar and pseudo higher order functions, but in effect they do the same thing as higher order functions in other language. So in the end, you will get the same result. It will look almost the same. There is no much overhead, except for having to add these functional type interfaces for some use cases, if it doesn't fit the normal unary, binary, or the function declarations. So for example, if you want to pass 3 arguments, then you have to write your own. So anything more than 2 arguments, you would have to write your own. And if it works with more than 2 type, then you would have to write your own. So those are the overheads compared to other functional languages. So the final thing would be referential transparency. So referential transparency is nothing but language's ability to not let you do data mutations, kind of. So pure functional languages like Haskell doesn't let you do assignments, and hence forbids data mutations. But an OOP language like Java actually encourages data mutations. So OOP is all about mutating, having your data in your objects and mutating them. So it's designed for with mutation in mind, and it's like almost like fighting against it when you are trying to do immutable code in Java. So the compiler wouldn't help you at all with this. So it is really easy to do accidental mutations in Java. I mean, and since Java also passes arguments by reference, except for primitives, everything is passed as reference. So that means it is even more easy to accidentally mutate something. You might be passing like an object to a pure function, and unknowingly you might be changing something. And a lot of inbuilt Java methods, right? Like the default Java methods could also be mutating methods. So you might be doing it accidentally. You might be passing a collection to your pure function, and you might be calling the sort method on that, and which it's a mutating method. So it's going to sort the collection in place, and since it's a reference, it's going to affect everything else. So it doesn't help. So in Java, it is extremely easy to do accidental mutations, and honestly, there isn't any way to prevent accidental mutations. And of course, Java provides the final keyword, but I am like, in my opinion, it's a joke. It's as useless as the const in JavaScript. Of course, it will prevent reassignment of the variable, but I don't think I don't think people normally make mistakes by reassignment. Most of the mutation mistakes comes from mutating reference. So the final keyword doesn't stop you from mutating a field inside a final object, right? So it still lets you do that, and there is no indication of you doing that, so that a compiler doesn't help you anyway there. So in the end, referential transparency is completely up to the developer. So if you're writing pure functions, it's up to you to make sure that you're not doing mutations. There is no way for the compiler. I mean, there's no way the compiler is going to help you in any case. So if you compare it like compare this with languages like other non-functional languages, like for example Go and Rust are imperative languages. Like they are majorly imperative, but they also let you do functional programming. But those languages actually give you greater control in ensuring that there is referential transparency. For example, in Go, you can pass arguments to a function by reference or by value. So you can choose to pass by value. That means you are not going to accidentally affect state outside of that function, right? So and Rust actually even goes a step further, because in Rust also you can pass everything by value or reference, but it goes a step further. Everything in Rust by default is immutable. So if you have to mutate something, you have to explicitly declare that to be immutable. So that holds true for variable declarations, passing variables to functions. So whatever it is, you always have to declare that something is mutable explicitly, which makes it extremely easy to write immutable code in language like Rust or even in Go. And the compiler will catch if you're accidentally mutating something. I mean, I have been doing Rust, like I'm building a project in Rust for like last few weeks, and there was there was not even a single instance where I accidentally mutated something, and it was a heavily concurrent application with shared state mutex data. So there was like no way I could do that in Java without having to spend a lot of time uh, finding out bugs that is accidentally created by accidentally mutating stuff, right? And in language like Rust, you can confidently go ahead and mutate stuff, and you can be sure that you're not accidentally mutating state outside of a function. So that is extremely nice. So it's hard to appreciate these kind of features unless you work on a language like that. So in Java, referential transparency is quite difficult. I would rank I would rank Rust and Go much higher than Java. Even JavaScript and TypeScript, sorry, not JavaScript, but TypeScript can be ranked much higher than Java when it comes to referential transparency. So this is the weakest part of Java when it comes to functional programming, and I think this is probably the reason that that you would end up spending much more time doing functional programming in Java compared to other languages. So yes, so Java can be functional style language if you are patient and disciplined. So like I'm not trying to say that you shouldn't be doing functional programming in Java. It is still much nicer to write declarative code using stream APIs and optionals than writing imperative code for most of use cases. But I don't think if you try to write 100% functional code in Java, I think you'll be fighting the language a lot, and I don't think you'll be as productive as like as productive as mixing both. Because Java is not a functional language. It's just a language that lets you write functional style code. So yeah, that's it. I hope this was useful in some extent. I also have the same. I also have a blog version of this. You can find it in my website under the functional tag. I have a blog for with similar structure for Java, TypeScript, Go, and Rust. So if you are interested to compare how this looks in these different languages, please check it out. And you can always reach out to me via Twitter or via my website if you have comments or questions. Of course, this was more for beginners kind of thing. If you're an expert, then you probably already know all this. So one thing I again want to highlight is probably the power of using lambdas for closures and the power of is it the power of using lambdas for closures and currying. So this is not something that normally people do in Java. I mean, at least I haven't seen. I mean, I have worked with a lot of Java code bases, and I have never seen anyone doing currying in Java. Whereas in like JavaScript and those kind of languages, it's extremely common to see currying. But I would say that this is something that you can actually use a lot in Java, and you can make your code much more dry with this. You can do a lot of code variations and do much more functional style of declarative coding using currying. So try to make use of currying. It's quite simple. I mean, there is no much overhead except for declaring this one, this kind of function, and that also with Lambda becomes much more concise. So it's not much overhead at all to do currying in Java. So thank you. I hope this was useful. Yeah, I can take some questions if you have any.
I haven't got any questions in the chat so far. Thank you very much, Deepu, for your very nice presentation. It was really good. And thanks also for the summarization. This is what Java is good at, and this is well, where you shouldn't do stuff like tail recursion or head recursion. I've seen it. I mean, I've done it in C, and yes, you fill up the stack and boom, your stack overflowed.
Yeah, I mean, in Java, it's even easier to do that, I think.
Okay.
Yeah. I couldn't go about 20.
No, absolutely not. I would.
20 is the maximum I could go with this.
Yes.
Yeah.
Oh, 20, and then it would just kill you.
Yeah, after 20, it just explodes. Yeah. with the normal recursion. So
yeah.
20 was the max.
Also, like you did other languages. What other languages? You said you work with Rust now. Go. Other languages you're working with?
Yeah. So I'm predominantly do Java, JavaScript, Go, and Rust. So that's my major languages. So I think, recently I have been doing a lot of Rust and Go. I was building a command line tool in Rust. It's a lovely language. I'm falling in love with it. It's really nice. And when I don't like languages which has a lot of I don't like Scala, for example. I find it. I know why people like it, but I don't find it very beginner friendly or like very readable. I have worked in teams where everything was in Scala, and like most of the time spent is trying to understand code. Because because of all that like implicit stuff. I mean, it doesn't have implicit state mutations, but there is a lot of implicit magic happening, right? Like for example, like all those what is that? I forgot what there is some implicit stuff that automatically applies to methods and stuff. Like it's quite hard to know that these stuff are even there unless you find a bug, or like then you don't even know. Like even the people who wrote that, like after a few years, like nobody, like everyone was looking into this one error. Like nobody understands why this happens. Like then like after like what day or something of debugging, then somebody, okay, there is this implicit transformation on this. Like okay, like why would you do that? Like so yeah, so like because I felt that all those extra semantic complexity probably wasn't worth it, because in the end it is still running on JVM. It's not like zero cost abstractions or stuff, right? And Rust also has similar complexities, not as complex as, semantics are not as complex as Scala in my opinion, but there is still a lot of complex semantics in terms of lifetimes and complex generics and stuff. But it is worth it in my opinion because of the zero cost abstraction factor and because of no garbage collection or anything. Like it just manages memory automatically, and like writing functional code in Rust is like really nice. It wouldn't let you you can explicitly write both in the same thing. I mean, it's not like fighting with Haskell when sometimes you have to do something non-functional and you have to spend fighting the language over it. Like it's not like that. I really don't like doing that, because I believe that there is use cases for both. Like functional program, 100% functional programming is not answer to anything. Same way OOPS was not the answer to everything 20 years ago. So yeah, this good mix is quite nice. Like you can choose to do both, but you can choose to do both in a really nice way. So that's quite nice.
You seem to have done a lot of languages. Have you learned a lot of different computer languages?
Yeah, I mean, Yeah, I really like trying out languages. And if I like the language, then I kind of stick to it. So I think I tried around 10, 12 languages, and these like Java, JavaScript, TypeScript, and Go and Rust are like my favorite.
Mm?
Kotlin is also nice, but I didn't get chance to do a lot of Kotlin except for some Android stuff. So, but it's nice. Yeah, I did some Groovy in the past, but it wasn't that impressive. I mean,
Mm.
it felt like just syntax sugar over Java, and Scala was not my cup of tea. So,
Okay.
but yeah, yeah, and of course there is Ruby, Python, on those stuff. Again,
Yeah.
I'm not a fan of
Yeah,
those.
yeah.
I tried, but yeah.
Would you say you become a better developer once you learned more languages, understanding the different structures and
Yes,
ups and downs of the languages?
yes, yes.
Yeah.
Yes, absolutely,
Brilliant.
absolutely. I mean, I was able to. I think there was things I learned from one language which I could apply to the other.
Mm?
Just have to change the semantics a little bit, but I could apply that to in other places. And I feel like once you learn 3 or 4 languages, then learning a new language becomes extremely easy,
Mm.
because in the end the principles are almost the same. It's just the syntax that differs and some new things that some language might offer. So you just have to learn that. For example, like learning Rust was quite easy for me because some things was quite similar to Go, which I already knew. So
Mm?
I didn't have to learn that part explicitly. The only thing I had to learn new was the lifetime and the ownership concepts. Everything else felt almost the same. I mean, there was a lot of similarities to TypeScript, which I could just reapply. Some similarities. I mean, generics was like as same as in Java, right? So except for some complexities in some places, which you wouldn't always do, like sometimes, which you can always get help from community in those kind of cases. But I think it definitely helped me become a better programmer. Definitely.
Yeah. Again, thank you very much for your presentation. Really like it.
Yeah.
Thank you very much.
Thank
And
you.
we will put
Yeah.
out all the
Yeah.
the sources, links to blogs and everything under the YouTube film once it's out. Yes.
Yeah. Thank you.
Thank you. And
See you.
that's yes, and that's it. We'll come back in 26th of May for another meetup. And if you have anything to present or you someone that should present, either poke them or poke me, and I will chase them up and get them here to present. And we can have people either on link or here in the studio in Stockholm. And that's it. And thank you for tonight. And thanks everyone for following all 3 presentations. Thank you very much.